Hey, what up? This is Yatin and welcome to Thermoforged. There is quite a buzz around thermoplastic composites, but the amount of information on the subject is a bit thin. This video intends on going into this subject and actually doing comparison between thermoplastic composites and what is conventional composite that most people are using. By the end of this, you should have an idea of what are the difference between these materials and where are the new opportunities that are arising from this. Let's have a look at the fundamentals. The definition of a composite is very simple. It is pretty much two or more material being mixed and used together. So the first part of a composite is the matrix. The matrix is pretty much the material that holds everything together. So it's kind of like the mechanical bond for everything else. For the purpose of this video, we're going to be thinking mostly in terms of fibers, but the second material can also be, say, particles, among other things, and the ratio between these two varies, but let's think of it as 50-50 for now. That ratio really varies. Now, there are three different types of composites. The first one would be the fiber reinforced plastics. So that's the main one, and that's what this channel, at least at the beginning, will be focusing on: fiber reinforced plastics. The second one are ceramic matrix composites. So think of ceramic being used in the applications where you need a lot of heat resistance. So a space shuttle, a gas turbine engine, or maybe the brakes of a high performance car. And you also have metal matrix composites. So that's where you have a metal instead of, say, the ceramic. And this is used in really harsh environments like a, say, nuclear reactor or somewhere where there's a lot of abrasion. But for now, we are going to focus mostly on fiber reinforced plastic because there's two categories on this. So there's thermoset composites, which is conventional composites, and thermoplastics. So if we focus for a second on thermoset, for the most part, thermoset composites exist in the format of a liquid, or generally speaking have very low viscosity. So it starts as a liquid and you will apply some heat to it, and the application of heat means that the material is going to cross-link and then the material solidifies. When you cool the material, it doesn't go back to being a liquid, it stays as a solid, so you can only cure it once. So a really good analogy on this is, think of it as an egg. You have the egg, starts as a low viscosity liquid, you apply some heat to it, it solidifies, and then it stays that way from now on. The other side of the coin would be thermoplastic composites, and thermoplastic composites are actually a solid at room temperature. You have to apply heat to it to get it to liquid state, and then actually it will re-solidify when you bring it back to room temperature, but you can do that over and over again. And the analogy here, it's very similar to butter, where butter is solid at room temperature, and then you can melt it and then put it in different shapes and remold it multiple times. So I think a really good place to start would be a bit of an explanation about why is it that thermosets are so popular and have been the main type of composite that have been used for decades and decades. So let's start for now looking at liquid thermosets. So I have this video here from Easy Composites, and what it is really showing us is, and I would recommend checking out the channel. So the guys at Easy Composites have a material here which is a liquid, and then this material gets mixed with a hardener, and the hardener over time will get the material to gel and then solidify. But this material, what's interesting is, so you have a tool which is under vacuum, and this material, because it's so low viscosity, is getting pulled as a liquid under vacuum, and the material is just literally slowly flowing through the tool and impregnating that particular material. So what's interesting about this is, generally speaking, you can have very complex geometry, you can have low cost tooling, and you will impregnate the whatever complex geometry that you have. You wait for material to gel and solidify, and then you can open up the bagging material, and then you can cure it afterwards in an oven. Generally speaking, the curing time on this is 6 to 12 hours. It can take a long time, but this is great for prototyping. There's a couple of manufacturing processes where this is getting used in production, and the cost on this is, generally speaking, quite low in terms of material cost. Thermoset prepreg. So that's another very popular format that this material is used. But the difference is, earlier you had a dry fiber that had to be impregnated through vacuum. In this case, this is a fiber that is already impregnated with resin. And you will see here that this material is very easy to process. So you can use a scalpel to cut it, or you can use scissors like you can see here. And the material is encased between two layers of protective film. So you remove a protective film, and then you can see this shiny carbon fiber underneath, which is impregnated with resin, and the resin itself is tacky. So it's actually quite friendly for you to be able to place in a mold and push it down and position it. The barrier to entry into the skill set can be fairly low, so you can learn how to use this material quite quickly. This is a lot more expensive than just buying the resin and just buying the fiber, but because it is so user-friendly to process, a lot of people use the material in this format, and then afterwards, when the material has been placed in an oven, it's cured, solidifies, and then we are good. Okay, so we had a look at conventional composites. Let me do a contrast into thermoplastic composites. In this case, let's look at the thermoplastic prepreg. So I have a picture here, which is, you have, in this case, it's a continuous fiber. It can be, to be fair, a fabric fiber or whatever it is, but it's a fiber that is encased in resin. In this case, we're looking at a thermoplastic resin. Now, what's different with the thermoplastic resin is, at room temperature, the material is solid. So you need to apply heat to the material to be able to melt it and then position it. And I have an interesting video here from the Fraunhofer Institute. So they're manufacturing a pipe here. And what you're seeing here is a material which is getting fed in, and you have a roller which is compacting it. So let me pause onto video for a second to explain exactly what is going on and why this is an interesting process. You have a material which is getting fed, so that's right here. You have the impregnated thermoplastic composite, which is again a solid at room temperature. It's getting applied onto this particular tool, and you have a laser that is melting locally, melting the material here, and the roller applies it there. So material is solid, the laser melts it so that it can tack onto the substrate, and then it instantly solidifies and stays there. Now, the reason why this is interesting is, if you were to make this pipe using a thermoset material, you would be using a similar type of machine, but the difference is the material would go on, but you would have to post-cure the material in an oven, take it out, and the bagging and all the cost that is involved. Whereas with a thermoplastic composite, the material gets consolidated locally in situ, and there's no curing required. And there's an opportunity to really save money here because it's so much faster and you need less equipment on the post-processing. Let's go on to another format of this material. So if you take multiple layers of that thermoplastic prepreg, you can actually build a thermoplastic panel. And that's a really nice picture that you can see here from Envalia. And really this material you can see to the right, what appears to be a recycled fiber material, but also you have different types of fabrics, discontinuous fibers and different types of fibers in here. And these materials are manufactured in big rolls, and you have rolls of panels of varying thickness which are made continuously, and then they get shipped to your facility where these are available stacked up. In this case, you can almost think of this as an extreme case, a very complex geometry. This is a front-end bolster for a vehicle which was made by the French company Valeo. And let me zoom into this material and I'll explain to you how this was manufactured. So what you're seeing here is you have a material which is all of this, probably by visually, it looks like a glass fiber material, and the resin impregnating it most likely will be a high temperature resin. This has been formed into multiple curvatures, and the way Valeo would have made it is the material comes in as a big panel that gets trimmed into the geometry that you can see there, into a 2D geometry. So the material gets trimmed and usually it's water jet fairly quickly. Material is heated up to past its melting point, and what it means is when it's past its melting point, the material is very soft and pliable. Once it's past melting point, the material is then inserted into a tool where the tool just presses it and forms it into place. So that's why you can see the curvatures on this. And in this case, they even over-molded, so they injection molded all around this geometry, multiple complex features. That's why you get to mount, you have mounting points on it, and then you have multiple complex geometries on it. And this whole manufacturing process, if you were to do it, say, for example, using a thermoset material, just the layup of the material and then the curing and then the overmolding, which is a bit more complex, all of that, you're thinking in terms of hours and hours, and I'm talking like tens of hours, which is very costly, whereas this manufacturing process is done literally in minutes. 3 to 5 minutes, you can actually make this part, which is incredible and makes it really suited for high volume manufacture. If you're making cars, you're making millions of cars a year, ideally you'd want this process rather than a process that takes 100 times longer. Okay, so if we were to summarize, the composites industry, for the most part, is really based around thermosets, and there's very good reasons for it. Because of the low viscosity of the material, it is a lot easier to process at room temperature, but it also comes with challenges. If you want to use a thermoset and do it at really high volume, say the energy industry, say even the aerospace and automotive and so on, the costs involved in scaling this up are very, very high in terms of processing costs. And that's where thermoplastic composite comes in. Thermoplastic composites, well, the thermoplastic itself is solid room temperature and softens up at when you heat it up. And what it means is the handling of this material is a lot easier than if you want to process it. The processing times is orders of magnitude faster. So for high volume application, if you're willing to pay a lot of money and invest in equipment, then you have a manufacturing process which is extremely fast, and then you recoup onto your investment for equipment. So the potential there is incredible. Thermoplastic composite is a subject that you can go a lot deeper into. And today you had an intro in terms of what is conventional composites and what are the opportunities with thermoplastic composites. And hopefully it should give you an idea of, if you have a product, which one is best suited for. So in the next video, I will be going in terms of what are the advantages and disadvantages of both material, and I will be thinking very deeply in terms of material properties, cost, manufacturing processes, and so much more. I can't wait to share this with you. If you don't want to miss out on this, I would strongly suggest click on the subscribe button, and I will see you then. Peace.